All right, let's get straight into it. Today, we are going to do something a little different. We're taking one single, huge exam question and pulling it apart piece by piece. We're talking about question 09 from a GCSE higher tier paper. And get this, it's worth a massive 18 marks. By the end of this, you'll see exactly how to read the data, ace the calculations, and describe the lab work to bag every last one of those marks. Ready? Let's go. So here's how we'll tackle it. First, analyzing the graph, then nailing the calculations. After that, we'll cover the titration method, and finally, we'll wrap it all up with some key exam takeaways. Okay, first section, analyzing the graph. This is all about interpreting the experimental data and really getting the science behind its shape. All right, take a look at this. This graph is the heart of the first part of the question. You can see we've got temperature on the y-axis and the mass of citric acid added along the bottom. And look at the trend. As we add more acid, the temperature drops, hits a low point, and then starts to creep back up. So what's going on here? The next few questions are all about figuring that out. And boom, first question. Suggest one reason for the anomalous point at 0.60 grams of citric acid. You see that point? It's just floating there, not following the trend at all. The question is clever. It tells us the student didn't make a mistake measuring or plotting it. So the mistake must have happened during the actual experiment. So what could have gone wrong in the lab? Okay, let's look at what the official mark scheme says. The accepted answers are things like didn't stir the solution enough, or they measured the temperature before the temperature stopped falling, which is basically the same as saying they measured the temperature too soon. See what's going on here? It's not about complex theory. The examiners want to see if you understand the messy reality of doing an experiment. It's a test of your practical know-how. All right, anomaly sorted. Now for the main event. Explain the shape of the graph in terms of the energy transfers taking place. This is a juicy 3-marker. We have to explain the whole thing, why it goes down and why it comes back up. And the key is to talk about energy.
So, to get all 3 marks, you need to hit 3 key points, just like the mark scheme lays out. First, you've got to say that the temperature goes down because the reaction is endothermic. It's literally sucking in energy from the solution, making it colder. That's point 1. For point 2, you need to talk about that turning point at 1.5 grams. That's when a reaction is over. All the sodium hydrogen carbonate has been used up. And finally, for the 3rd mark, you explain why the temperature goes back up. Well, the reaction stopped, so now the cold beaker is just warming up to room temperature. It's taking in energy from the surroundings. Nail those 3 points, and you've got it.
Okay, next up. This is a classic what-if question. What would the line look like if a metal container was used instead of polystyrene? Explain why. So we're swapping out our cozy insulated cup for a metal one. How's that going to change our graph? And you've got to explain why. Right, let's break it down. Think about it. A polystyrene cup is a fantastic insulator. That's the whole point of using one. It keeps the inside separate from the outside, so less energy gets in from the room. That's why you get a nice, steep temperature drop. But a metal container? That's a totally different story. Metal is a great conductor. It would be constantly letting heat from the room leak into your cold solution, basically working against the reaction. So what happens? The temperature drop you measure would be way less steep. It wouldn't get as cold. All right, we've dealt with the graph. Time to switch gears and get into the math. Part 2, nailing the calculations. We're going to go step by step through all the titration maths here. So here's our first task. We need to calculate the mass of citric acid required to make 250 centimeters cubed of a 0.0500 mole per dm cube solution. They give us everything we need, the formula, the volume, and the concentration. Let's do this. It's a 3-step recipe, and you've got to show your work for each one. Step 1, work out the MR of citric acid. You just add up the atomic masses from the periodic table, and that gets you 192. Easy. Step 2, calculate the moles. The formula is moles equals volume times concentration. Now be careful, the volume is in centimeters cubed, so you must divide it by 1,000 to get it into dm cubed. That gives us 0.0125 moles. And finally, step 3, you find the mass. Just use the formula mass equals moles times MR. So it's 0.0125 times 192.
And that gives us our final answer, 2.4 grams. See, showing those steps is absolutely key to getting all the marks.
Okay, now for the big one, the main titration calculation. Calculate the concentration of the sodium hydroxide solution. We're told that 13.3 centimeters cubed of our citric acid solution neutralized 25.0 centimeters cubed of the sodium hydroxide. We know everything about the acid, but we need to find the concentration of the alkali. This is where we put it all together. Again, it's a step-by-step process. First, find the moles of the thing you know everything about, the citric acid. Volume divided by 1,000 times concentration gives us 0.000665 moles of acid. Now for step 2. This is the most important part. You have to look at the balanced equation, which tells you it's a 3-to-1 ratio. For every 1 mole of citric acid, you need 3 moles of sodium hydroxide. So we just multiply our moles of acid by 3. That gives us 0.001995 moles of NaOH. Finally, step 3, we find the concentration. We just rearrange the formula. Concentration equals moles divided by volume. And remember to convert that volume to dm cubed again.
Plug those numbers in and you get your answer, 0.0798 mole per dm cubed. You know, it looks complicated, but when you break it down into those clear steps, it's totally doable. Just follow the process.
So we've crunched the numbers, but those numbers come from an actual experiment. So let's move on to our next section, the titration method. It's time to talk about the practical side of things. Okay, another 3-marker here. The question asks you to describe how the student would complete the titration. Imagine you've got your burette and flask all set up. What do you actually do to get your results?
The mark scheme wants 3 clear steps. Step 1, you add the citric acid from the burette into the flask bit by bit until you get a permanent color change from the indicator. Step 2, you carefully read the burette and record that volume. Step 3, and this is crucial for accuracy, you repeat the whole thing until you get concordant results. That's the magic phrase. It just means results that are really close to each other. Then you find the mean. And of course, don't forget the pro tips: always swirl the flask, use a white tile underneath to see the color change clearly, and add the acid drop by drop when you think you're getting close to the end.
All right, final practical question. Give 2 reasons why a burette is used for the citric acid solution. I mean, why go to all that trouble with a burette? Why not just use a measuring cylinder? What makes it so special? Well, here's what the mark scheme says. It all boils down to accuracy. First, a burette can add the solution in very small increments. You know, drop by drop. That's essential for finding the exact endpoint. Second, it can accurately measure variable volumes. You're not just measuring out a fixed amount. You're measuring exactly how much you used, whatever that volume turns out to be. And finally, you could just say it's more accurate than other apparatus, like a measuring cylinder. Pick any 2 of those, and you've got the marks.
And that's it. We've made it through the entire question. Let's zoom out a bit for our final section. Key exam takeaways. It's amazing how many different skills are packed into just one question. Just look at everything we've covered. We've done interpreting graphical data and spotting anomalies. We've explained energy changes and reactions. We've talked about heat transfer with insulators and conductors. We've performed 2 different solution calculations for mass and concentration. We've described a practical lab procedure, titration, and we've applied stoichiometric ratios from equations. It's a whole checklist of skills. This really shows you why just practicing these huge questions is one of the best ways to revise. It pulls everything together.
So we're at the end, and hopefully seeing exactly how those 18 marks are awarded gives you a new perspective. You see, it's not just about knowing the facts. It's about showing your working, understanding lab errors, and connecting the dots. So I'll leave you with this question to think about. Now that you've seen this breakdown, what part of your own revision are you going to approach differently? Is it the maths? The practical stuff? Think about it, because understanding how you're tested is half the battle. Thanks for sticking with me, keep up the great work, and I'll catch you on the next one.